Quantum catalysts and nanocatalysts represent some of the most exciting advances in modern chemistry and materials science. Recent achievements in this field include the design of catalysts at the atomic and molecular scale that are capable of dramatically lowering reaction barriers and improving efficiency. For example, researchers have developed nanocatalysts composed of platinum or palladium nanoparticles that significantly enhance reaction rates in fuel cells and industrial chemical processes. How do these tiny catalysts work so effectively? Their high surface-to-volume ratio ensures that a larger proportion of atoms are available to participate in chemical reactions, while quantum effects can further modify electronic properties in ways that optimize catalytic performance. Despite these promising results, there remain significant challenges. One key issue is the stability of nanocatalysts over time. At the nanoscale, catalysts can be prone to aggregation or sintering under reaction conditions, which diminishes their surface area and, in turn, their catalytic activity. Researchers are actively exploring methods to stabilize these catalysts, such as using supports or creating core shell structures that protect the active sites without impeding performance. Another challenge involves scalability. While many quantum and nanocatalysts show remarkable performance in laboratory settings, transferring these successes to industrial scale processes is often fraught with difficulties. How can we bridge the gap between experimental breakthroughs and real-world applications? Overcoming these challenges is essential to harness the full potential of these advanced catalysts. The fundamental significance of quantum catalysts and nanocatalysts extends beyond their immediate applications. At the quantum level, these catalysts provide insights into reaction mechanisms that cannot be fully understood through classical models. By studying how quantum tunneling, discrete energy states, and electron delocalization affect reaction pathways, scientists can refine theoretical models and develop new design principles for catalytic materials. For instance, investigations into plasmonic nanocatalysts have revealed that localized surface plasmon resonances can create hot electrons, which in turn drive chemical reactions at lower temperatures and with greater selectivity than conventional catalysts. Could these discoveries reshape our approach to energy conversion and chemical synthesis? The emerging evidence suggests they might, opening up avenues for more sustainable and efficient industrial processes. Moreover, these catalysts have the potential to transform fields as diverse as environmental remediation and renewable energy. Nanocatalysts can be engineered to break down pollutants in water or air, and quantum catalysts might enable new pathways for carbon dioxide reduction, contributing to climate change mitigation. Their ability to function under milder conditions not only reduces energy consumption, but also minimizes harmful byproducts, making chemical processes greener and more economically viable. Current achievements in quantum and nanocatalysts highlight their ability to enhance reaction efficiency and selectivity through both classical and quantum mechanisms. However, challenges related to stability, scalability, and practical integration remain significant obstacles. The fundamental significance of these catalysts lies in their dual role as tools for transforming industrial processes and as windows into the quantum nature of chemical reactions. Could ongoing research in this field eventually lead to breakthroughs that revolutionize how we approach catalysis in energy, environmental, and industrial applications? The progress so far suggests that the future holds exciting possibilities for both scientific discovery and practical innovation. Quantum catalysts and nanocatalysts are revolutionizing chemical reactions by leveraging quantum mechanical effects at the nanoscale. As quantum tunneling, electron confinement, and surface plasmon resonance allow for precise reaction control, these catalysts exhibit enhanced reactivity. Unlike traditional catalysts, nanocatalysts have high surface area to volume ratios, increasing the number of active sites. Researchers are currently exploring how quantum effects in nanoparticles improve selectivity and efficiency in industrial and energy processes. Palladium nanocatalysts have been shown to accelerate hydrogenation reactions at lower temperatures compared to bulk palladium catalysts. Quantum catalysts function like a microscopic chef that can cook food at lower temperatures by arranging molecules in just the right way. Quantum tunneling allows reactants to bypass traditional activation energy barriers by tunneling through them rather than going over them. This effect significantly enhances reaction rates, particularly in hydrogen reactions and enzyme catalysis. Nanoparticles exhibit this behavior due to their confined electron wave functions, making quantum tunneling more probable. This is especially relevant in biological systems where enzymes use quantum tunneling to speed up biochemical reactions beyond classical limits. Hydrogen transfer in enzymes such as alcohol dehydrogenase demonstrates quantum tunneling, allowing for efficient metabolic reactions. It's like a ghost walking through a wall instead of having to climb over it, a shortcut that speeds up chemical reactions. Quantum confinement occurs when electron movement is restricted to nanoscale dimensions, modifying the electronic properties of catalysts. This leads to tunable catalytic activity where the size, shape, and composition of nanoparticles directly impact reaction pathways. For example, smaller nanoparticles often exhibit lower energy barriers for oxidation and reduction reactions due to altered electron density distributions. By controlling these parameters, researchers can design catalysts with unprecedented efficiency and selectivity. Gold nanoparticles under 5 nm exhibit catalytic properties that bulk gold lacks, making them useful in carbon monoxide oxidation reactions. It's like squeezing an orange. The more confined it is, the more juice is available to drive chemical reactions. Surface Plasmon Resonance, SPR, occurs when conduction electrons on a nanoparticle oscillate in response to light, enhancing catalytic efficiency. This effect allows for photon-driven catalysis, where light energy is used to activate and control chemical reactions without the need for high temperatures. Plasmonic nanocatalysts, such as gold and silver nanoparticles, have been used in CO2 reduction, water splitting, and organic synthesis. SPR-based catalysis offers a promising route for sustainable energy applications. Gold nanoparticle plasmonic catalysts enable CO2 to be converted into useful fuels using only sunlight. It's like a solar panel on a molecular scale using light energy to power chemical transformations. Nanocatalysts play a critical role in energy conversion, from hydrogen fuel cells to carbon capture and conversion technologies. Their high catalytic efficiency allows for cleaner energy production with minimal waste. In petrochemistry, they enhance the efficiency of cracking and reforming processes, leading to lower emissions. In green energy applications, nanocatalysts facilitate reactions like water splitting to produce hydrogen as a clean fuel. Platinum-based nanocatalysts are widely used in hydrogen fuel cells to improve reaction rates and durability. Nanocatalysts work like an ultra-efficient chef in a restaurant, preparing meals faster and with fewer ingredients wasted. Despite their promising properties, scaling quantum and nanocatalysts from laboratory synthesis to industrial-scale applications is challenging. Issues include catalyst degradation, high production costs, and difficulties in maintaining nanoscale control in large-scale manufacturing. Stability is another concern, as nanoparticles can aggregate or undergo chemical changes over time, reducing efficiency. Researchers are exploring new support materials, coatings, and synthesis techniques to enhance durability and scalability. Titanium dioxide nanocatalysts are widely used in photocatalysis, but their performance often declines over time due to recombination effects. It's like trying to mass-produce handcrafted jewelry. Scaling up requires maintaining precision and quality, which is difficult at large volumes. Nanocatalysts contribute to sustainability by reducing the energy input required for chemical reactions and enabling cleaner processes. They are used in environmental remediation to degrade pollutants, break down toxic chemicals, and purify water. Photocatalytic nanomaterials such as titanium dioxide can decompose organic pollutants under sunlight. These advancements align with global efforts to achieve net zero carbon emissions and develop eco-friendly industrial practices. Silver nanoparticle catalysts are used in water purification systems to break down organic contaminants and kill bacteria. Nanocatalysts act like microscopic cleaners, scrubbing pollution away at the molecular level. Quantum catalysts are transforming synthetic chemistry by enabling selective and highly efficient reactions, reducing the need for toxic reagents. By leveraging quantum coherence, catalysts can be designed to drive reactions with precise molecular control. Quantum-enhanced reaction pathways are being explored in pharmaceutical synthesis to create complex molecules with higher yield and purity. Future advancements may involve AI-driven catalyst design, optimizing performance based on quantum simulations. Nanocatalysts are used in asymmetric synthesis, allowing for the precise production of chiral drugs with minimal waste. It's like having a molecular sculptor who can carve out the perfect chemical structure with minimal mistakes. The study of quantum catalysts and nanocatalysts provides deep insights into fundamental physical and chemical principles. Understanding how quantum mechanics influences catalysis at the nanoscale enhances our ability to design materials with unprecedented properties. These materials bridge the gap between classical and quantum chemistry, opening new frontiers in energy, medicine, and advanced manufacturing. Their impact on fundamental research extends to quantum computing, molecular electronics, and next-generation materials science. Quantum dot catalysts are being investigated for their role in bridging the gap between molecular electronics and catalysis. It's like unlocking a new dimension of chemistry, where the smallest changes create massive transformations in how reactions occur.